Assalamualaikum warahmatullahi wabarakatuh. We are from Group 2 in Section 4 and now we're going to present an application of second order linear differential equation which is the fin equation. My name is Muhammad TAUFIQ HAKIMI bin JAMIL with matrix number DD250120. So for the introduction, when we look at the motorcycle engine, computer or refrigerator, we often see metal structure that are layered or arranged in many thin sections. They look similar to a comb or stacked metal plates. We call this structure as fins. The main purpose of this fin is to increase the surface area exposed to the surrounding air. Logically, when the surface area becomes larger, more heat can be transferred to the air. The greater the heat transfer, the better the cooling effect. This will help reduce the temperature of the component and prevent overheating. That is why engineers design structure like in this image. This diagram shows a fin attached to a hot surface. The temperature at the base of the fin is represented as T base or T subscript B, which is the highest temperature in the system. Heat will flow from the base toward the tip of the fin through conduction. At the same time, heat is continuously released from the fin surface to the surrounding air by convection, where the surrounding temperature is represented as T subscript infinity. As heat is lost to the air, the temperature gradually decreases from the base to the tip of the fin. The purpose of the fin equation is to determine how this temperature changes along the fin and how much heat is transferred to the surrounding. To simplify the mathematical modeling, we assume steady state condition, one-dimensional heat conduction, constant thermal conductivity, uniform convection coefficient, no internal heat generation, no radiation heat transfer, and adiabatic fin tip.
Assalamualaikum, my name is JAZMI bin JASMAN and my matrix number is 8DD250131. So I will explain about the derivation of the equation of ODE. To get this equation, we start with an energy balance on a tiny slice on the fin. Heat flows in one side and out the other, and some escape sideways into the air. So the equation that we got is Qx equals to Qs dx plus dq convection. So after we got the equation, we got the input, which conduction is given by Fourier law, where Qx equal to negative Ka multiplied by dt over dx. The heat leaving the slice Qs dx is just Qx plus a small correction term from a Taylor expansion. And the convective loss is given by Newton's law of cooling, where dq convection equals to Hp dx multiplied by T minus T infinity. After we substitute the input into our equation, these are the simplify. After we simplify the equation, that we got the Qx term cancel and we are left with d square T over dx square equals to Hp over Ka multiplied by T minus T infinity. And we define our equation into theta equals to theta T minus T infinity, which means how much hotter the fin is than the surrounding in the air. The bundle right constant into m square equals to Hp over Ka. That gives us our final equation, which is d square theta over dx square minus m square theta equals to 0. So now I will explain about how we solve the equation with the characteristic equation. We start with the d square theta over dx square minus m square theta equals to 0. To solve it, we guess theta equals to ERX. We put that in, give the characteristic equation equals to r square minus m square equal to 0. So r equals to plus m or r equal to minus m. With two real roots, the solution is built from E mx and E negative mx. We rewrite this in cos h or and sin h for convenience, giving the general solution. So the final solution that we got is the theta x equal to a cos h mx plus b sin h mx. A and b are still unknown. We will find those next from the boundary condition.
Okay. Hi, my name is Muhammad Ramdhan Zakaria. My matrix number is DT250128. Okay. Let's move to the applying boundaries condition. After obtaining the general solution for the fin temperature distribution, we apply the boundaries condition to determine the unknown constant. For boundaries condition A, at the base of the fin where x equal to 0, we assume a Dirichlet condition, meaning the base temperature is fixed and equal to the wall temperature, T sub B. Therefore, the excess temperature at the base is theta 0 equal to theta B. Substituting this condition into the general solution gives us the first constant, where A equals to theta sub B. Okay, for boundaries condition 2, at the fin tip where x equal to L, we assume an adiabatic or insulated tip, meaning no heat is lost from the end surface. This is represented by the Newman's condition, where temperature gradient at the tip is 0, del theta over del x equal to 0. Applying this condition to derivative of general solution allows us to determine the second constant, give B equal minus theta sub B tan H ml. Okay, by applying these two boundaries conditions, we obtain a complete temperature distribution equation that accurately describes how temperature varies along the field.
Hi, Assalamualaikum. My name is Mohd HUSNAN bin ASRAFF, number metric DD250088. So, for my part, I'm going to explain about final temperature distribution and heat transfer. For the temperature distribution formula, theta x equal to theta b times cos h bracket m times L minus x over cos h times ml. So for the total heat transfer rate formula, we're gonna use QF equal to square root HPKA times dengan theta B times dengan tan H times ml.
Okay, so let's move to the efficiency and material effects. Okay, first, material comparison based on thermal conductivity. We have copper. The thermal conductivity is 401 watt per meter Kelvin. It is best performance. However, the copper is relatively expensive. Okay, for aluminium, the thermal conductivity is 205 watt per meter Kelvin. It is best balance, cost, performance, and weight. This is also the material that usually used in the industry. Okay, for carbon steel, it is the thermal conductivity is 50 watt per meter Kelvin. So this material is poor for the fin. So the last one is stainless steel, 15 watt per meter Kelvin. It is very poor and the thermal conductivity is very bad. Okay, so let's move to the effect of convection coefficient. Okay, H equal to 10 watt per meter square Kelvin. Natural convection, the tip is 89 degrees Celsius. When H equal to 50 watt per meter square Kelvin, it is moderate force because the tip is 58 degrees Celsius. For the H equal to 200 watt per meter square Kelvin, it is have high airflow and the tip is just 31 degrees Celsius. So the conclusion is higher H equal to steeper gradient equal to more heat removed.
Assalamualaikum. My name is Muhammad RIFQI bin ADZLAN with a metric DD250147. So for our real world application, we look at an A-cooled motorcycle engine. The label fins point to the metal ridge located on the engine cylinder and cylinder head. In this image, which resemble a motocross style engine, these fins are cast directly into the metal surface. Their purpose is to increase the surface area of the engine exposed to the surrounding air. The more surface area available, the more heat can be transferred from the engine to the air. The label air cooling refers to the processes where cool air from outside enter the fins gaps, blows over the hot fin surface, absorb heat from the fins, and then leave as hot air. This continuous airflow removes heat from the engine and keep it from overheating. Now let us trace the complete heat transfer part. First, fuel combustion inside the cylinder produces extremely high temperature. Second, heat conduct through the cylinder wall to the base of the fins. Third, heat conducts along each fins from the base toward the tips. Finally, heat convert from the fins surface to passing air, which carries the heat away. This is exactly the process modeled by the fins equation we derived earlier, where the fin increases surface area to maximize heat transfer to the surrounding air.
So for the conclusion that we got from the fin equation, we got ODE equals to theta square minus m square theta equal to 0. And the solution is in cos H form. So for the heat transfer, QF equal to tan H times ml, and the best length for ml is equal to approximately around 1.4 minus 2. And for the best material, uh, the that used for the fin is aluminium. Thank you.